Okay, sorry. Okay. So once again, good morning to all the participants connected with us on this virtual platform, and welcome to the fourth-day talk of ESTC, Current Trends on Condensed Matter Physics. So today we have a highly decorated condensed matter physicist and epitome of women's strength, Professor Sumathi Rao. She is currently a professor H+ at Harish Chandra Research Institute. Welcome, madam. Thank you, madam, for willingly accepting our invitation, for being here with us today. Madam, your presence here is truly momentous for us and very encouraging for all the participants. Professor Sumathi Rao completed her undergraduate education from Maharaja Sayaji Rao University at Vadodara, postgraduate education from Indian Institute of Technology, Mumbai, and PhD from State University of New York at Stony Brook, USA. She was a postdoctoral fellow at Fermi Lab in Chicago from 1983 to 1986, and a postdoctoral fellow at the University of Wisconsin at Madison from 1986 to 87. She has supervised 12 PhD with 60 research publications, a dozen of journal articles, and 2 books in her academic round. Her research interests cater to the field of correlated mesoscopic physics in low dimension like graphene, topological insulators, spin liquid phases, quantum Hall effect, and non-abelian statistics. She has been associated with innumerable national and international institutes of repute. She has served as a member of various scientific councils. She was a senior associate at International Center for Theoretical Sciences, Tata Institute of Fundamental Research, Bangalore, Fellow of National Academy of Sciences, Allahabad, Associate of Abdul Salam International Center for Theoretical Physics, J. National Science Talent Scholarship, Gold Medal, first in university during her bachelor's, Department of Physics at Maharaji Sayaji University, Vadodara, and many more. So it's a matter of great privilege to have such a decorated scientist among us. Without much delay, I invite Professor Sumathi Rao to bless us with her pearls of wisdom at the first talk for today's session of this ESTC. Madam, please.
Thank you very much for inviting me. Let me first present my Okay. Is my screen visible?
Yeah. Yes, madam.
Okay. Let me start by first thanking the organizer, in particular Professor Vinod Ashokan, for inviting me to give this talk at NIT Jalandhar. I will be talking today about topological phases of quantum matter, and I'm essentially trying to give my talk to the students. So if they're experts in the field, please excuse me for repeating things which may be obvious. Some of you probably know that the 2016 Nobel Prize in Physics was awarded to David Thouless, Duncan Haldane, and Michael Kosterlitz for theoretical discoveries of topological phase transition and topological phases of matter. Although this was the first Nobel Prize to actually mention topological phases, it's really not the first Nobel Prize for topological phases. In fact, the first was in 1982 to Klaus von Klitzing for the discovery of the quantized Hall effect, which of course now we know that that is the first example of a topological phase. The second one was in 1998 to Laughlin, Stormer, and Tsui for the discovery of a new form of quantum fluid with fractionally charged excitations. And this is the fractional quantum Hall effect. And I confidently say that one can expect many more in the future because according to a recent paper in Nature in 2019, roughly 1/4 of the topological of the materials in the world are topological, and roughly half of them, 12%, are topological insulators. And this is the reason that we are now having entered an important era of topological material design. And so one can expect there will be many new phenomena which we have not yet seen, and many more Nobel Prizes for topological materials in the future. With this, let me come to the plan of my talk. Essentially, what I want to talk about is the development of the field of topological phases in the last 40 years, starting from quantum Hall effect to topological insulators and topological superconductors, to Majorana modes, anyons, and finally to Dirac and Weil semimetals. And I'll end with the discussion of the current frontiers in the field. And I'm hoping that even if many of these words are now unfamiliar to many of you, by the end of the lecture, at least I will have given some idea of why these things are interesting to study. So with that, let me start with the basic idea of what are phases of matter, because I first want to define what is a topological phase. Of course, all of you are familiar with states of matter like gas, liquid, and solid. If you reduce the temperature of water, it freezes, it becomes solid. If you increase the temperature of water, it boils and turns into vapor. So these are different phases. So a phase is essentially a collection of particles with some property that distinguishes them from other phases. For instance, besides the solid liquid gas transition, earlier, even in various condensed matter systems, phases were classified in terms of symmetries. For instance, if you have a paramagnet with spins pointing in arbitrary directions, then you apply an external magnetic field, all the spins point in the same direction. So basically, this is called a ferromagnet, and it breaks the rotational symmetry in this spin space. But in the last 10 to 15 years, there's been actually a paradigm shift in the way of classifying phases. And now the phases are classified in terms of topology, or more correctly, I should say, on the interplay of topology and symmetry. And before I go on to define topological phases, why are they interesting? Well, new phases of matter are always exciting, but these have some particular features as well. They have excitations which can obey unusual statistics. They can have anyonic excitations and also excitations which have what are called non-abelian statistics. I won't go into detail of this, although I'll mention it again later. These are actually expected, these are the Majorana modes, and they're expected to be relevant in making fault-tolerant quantum computers. That is, you have qubits which cannot be destabilized by local perturbations. Because these Majorana modes are essentially things which are non-local in nature. They are spread out over space, so some small disturbance at one space cannot change them. And this is kind of the holy grail now of making quantum computers. So that is one reason that people have tried to understand topological phases in great detail. In fact, besides these anyons, there are various other exotic excitations like monopoles, dions, axions, etc., which actually may be found in these phases in low energy condensed matter systems. Earlier, all these things were studied in high energy particle physics. And in fact, this also tells you something about the unity of physics, because it's good for, all these things get connected. You may study something. I started my career as a high energy physicist, and I used to study monopoles and dions and axions then. Now you find that these kinds of excitations can actually be found in low energy condensed matter systems. So, what are these kinds of, why are excitations in solids different from the kind of elementary particles that we study in high energy physics? These excitations are not elementary particles, in fact, they're quasi-particles. They behave as if they are particles, even though they're a complicated mess. And to understand this, one needs to understand the miracle of what is called emergence or emergent particles. That is, from a complicated mess, you can sometimes have things which you can describe in a very simple way. A many particle system can conspire to behave in a very simple way. For instance, when you think of electrons lighting a light bulb, one can think of electrons as a flow of little particles, elementary particles. But of course, we know that through a conducting material. But of course, we know that these are wrong, because actually even something like a simple lithium atom, electrons in a single lithium atom are not really simple. Here we've shown the probability density of electrons in a lithium atom. The yellow color is the two electrons which are close to the nucleus. The blue color is this is an illustration, of course. It's further, it's just the density of the electrons being shown. But precise structure of electron densities, even for the simple atom, is not exactly known. More so when they are all put together to form a crystal. And so how does actually an electron, which is kind of flow through this mist? It gets pushed around by the nuclei, it will get pushed around by other electrons, so it will have a pretty chaotic trajectory. And if you think of more complicated metals like copper or silver, it only gets worse. So electrons actually, how do they flow in a wire? In terms of probability densities, it is like you're adding an electron to a wire, and then somehow the probability density propagates through. So the miracle is that we can think of the moving object as a particle, as a new kind of electron, a quasi-particle or collective excitation, which is made up of all the electrons. It's still an electron, called an electron, because it behaves like a particle. It has a mass, which may be different from the original mass, but it has the same spin and the same electric charge. So it behaves like a single particle. In fact, the correct analogy is to think of bubbles in a liquid. They're not really independent objects, but exist only inside the liquid. But a bubble acts as if it was a particle. It moves, it bounces off other particles, etc. It's a collective excitation. So quasi-particles in condensed matter systems are like that. They're not like the elementary particles that we have in particle physics. They're fundamental emergent excitations and emerge from a soup of particles. The early examples are quasi-electrons from electrons, which explain current flow. Phonons from the vibration of atoms explain sound and conduction of heat. Also other quasi-particles like magnons and protons in spin systems. In these topological phases, what happens is that you have Dirac electrons, Weil electrons, the Majorana particles, and other kinds of all these exotic excitations that I talked about in ions, axions, and monopoles. So these are all now collective excitations.
May I interrupt, madam?
Sure.
I think you'll have to again share your presentation. Someone had interrupted and
it has stopped sharing.
Stop and then again share it.
Okay.
Actually, it is visible to me. One has to pin it.
Sharing. Now I'll do present share again.
Hello.
Can you see it now?
Yes, madam, it is okay. I request you, the participant, please don't press the present now button, okay? So that will disturb the flow. Please. Yes, madam, it is visible now. You can make it.
I can make it full screen? Yeah.
Full screen. Yeah, yes, madam.
Yeah, so what I was talking about is quasi-particles in condensed matter systems, where what I was trying to say that now you have Dirac electrons, Weil electrons, and all these things which are present in these new phases as collective excitations. So I've been talking about topological phases. So what is topology? It's actually a branch of mathematics which deals with shapes. It tells you what remains the same and what changes. And topological implies that things should not be changed by small perturbations. And in fact, they should depend on the system as a whole. For instance, if you look at the picture on the right, in the first part, you can see that there is a circle around a point Z0. And there's something below it which says the index of Z0 is -1. And then you can see that this circle has been kind of twisted around, but still this particular curve goes around the point Z0 once in a clockwise direction. On the other hand, in the third figure, it doesn't enclose the point at all. So then the index will change. So in this particular example, what is important is whether or not this point Z0 is enclosed and in how many times and in which direction. For instance, these have indices -1, this has 0. This where it goes in the opposite direction has a +1. This where it goes twice around it has +2. So there is some integer associated with how many times the curve encloses the point Z0. For instance, and similarly, if you take a two-dimensional surface, you can think of plasticine or something like that, or dough. And then essentially, if you can just, by changing the shape of the dough, you can make it into a rectangle or even a glass. But to go from here to the to the donut, you actually have to punch a hole. And that is like making a drastic change. Whereas if you just kind of, without making holes, if you change it around, they are all in the same topological class. These three are in the same topological class. The ones with two holes are in the same topological class, and so on. So this is what defines topology in mathematics. In condensed matter systems, more technically, the kind of mappings that we'll be considering here, the mapping is just the function is just a curve or a surface. The kind of functions we'll be thinking about are mappings from one space, which could be just like this 2D space with a point removed, to the space of wave functions, and they will be classified by a topological invariant, which is the winding number. In this case, this is something called the winding number. In other mappings are classified by other number. In the quantum condensed matter system, the base space turns out to be something called a Brillouin zone, which could, for instance, be a torus in momentum space. And mappings are from the Brillouin zone to the space of wave functions. So essentially, the definition of a topological phase is that it has some physical property to which an integer can be assigned. The function has some integer assigned to it. And that will depend only on global properties and cannot be destroyed by impurities or disorder. And the first physical example that comes to mind is conductance in the quantum Hall effect. So to explain this, let me start with the first topological phase 40 years ago, which is the integer quantum Hall effect. All of you are familiar with the conventional Hall effect, which is basically just the idea that you have electrons, a current, flowing through a rectangular slab, and which is with a magnetic field perpendicular to the slab. And the forces are just the standard electric force and the Lorentz force, QV cross V. And in the steady state, since charges are not moving, essentially, charges are not moving perpendicular to the current. The current is moving in this direction, but there are no charges moving in this direction in the steady state. Because of this Lorentz force, what happens is that there is a charge buildup in this direction, and this is exactly what is known as the Hall voltage. And you can you must have done this earlier, that the Hall voltage is proportional to the current and the magnetic field. And this is normally how you find out the sign of the charge of carriers, because if it's electrons, it will go in one direction. If the charge carriers are opposite, it will go in the other direction. So the Hall voltage is something, Hall resistance is something which is the Hall voltage in this direction divided by the current in this direction. And it's given by Bz by NdQ. So according to the classical picture, the Hall voltage should be perpendicular, should be proportional to the magnetic field. However, when this experiment was done in a 2D system and at very low temperatures and in high magnetic fields, what they found is that instead of having a straight line, which is what would have been predicted by classically, what you got was actually, you found that there were the Hall resistance, which is the rho xy, was had plateaus exactly at integer values of e squared over h. That is, the conductance had values of integer times e squared over h. The resistance will be 1 upon that. So it's 1, half, 1/3, etc. in the resistance. What is plotted on in green is actually the linear longitudinal resistance. And what was seen is that whenever the Hall resistance was in a plateau, the longitudinal resistance was 0. So you would get current flowing without any resistance. And the longitudinal resistance changed and had peaks only when the Hall resistance changed from one plateau to another. This unit of resistance is now called von Klitzing, h by e squared, and it is known to a very, very high degree of accuracy and measured, in fact, in these kinds of experiments. So this was something which was first measured by von Klitzing in 1982. It's a phenomenon that occurs in two-dimensional electron systems at low temperatures and in the presence of small, strong magnetic field. And as I said, the Hall conductance is quantized in terms of integers, and the longitudinal resistance is 0, except when the Hall current changes from one integer to another. To understand this, one needs to have a use quantum mechanics, and at some level it depends. For the integer quantum Hall effect, it is the problem that you have to solve is that of a single electron moving in a perpendicular magnetic field, which is something that you probably would have done in your classes. It's just h psi is p minus ea squared by 2m psi, and you have to find out the energy levels. And the energy levels are highly degenerate Landau levels. They're highly degenerate because they depend only on the Landau level index n, and they're completely independent of the momentum in the x direction. So, and omega here is the cyclotron frequency EBZ by n. And so if you plot the Landau levels, you just have equispaced Landau levels, because ultimately it gets mapped to a harmonic oscillator. So you might naively think that you put the Fermi level over here, you should get no current. It should be an insulator. But as we already know, I mean, I've already plotted for you how the current changes, right? You do get Hall current perpendicular to the electric field. Essentially, you can't just take this picture, it's a bit too naive. You have to also include disorder in the picture. When you also have disorder in the picture, what happens is that, okay, here I've looked at the energy of the Landau levels, and then I've also calculated the degeneracy of the Landau levels in a finite area. And the degeneracy factor is something which is called nu, which is given by n, the number of electrons over EB by HC, which are the number of flux quanta. And in the presence of, so this was the plot that I had given earlier, but now you also include disorder in the picture. And in the presence of disorder, you have both localized and delocalized states. And what you find is essentially that when the Fermi level goes through here I plotted density of states against the Fermi level. When the Fermi level goes through delocalized states, these are the things, here are the localized states, and in the center here are the delocalized states. So when the Fermi level goes through the localized states, then you get a plateau. When it goes through the delocalized states, then you can jump to the next plateau. So this is the picture which explains why you get the Landau level picture that is found experimentally. The points to note is that when the density of electrons is such that an integer number of Landau levels is completely filled, then the state is stable. There's a gap to excitations. Due to disorder, there are states in the gap, but these do not conduct electricity, and it's only the states in the center of the band which can carry current, which is quantized. So the remarkable, this is not particularly remarkable. The really remarkable fact is that the quantization is so extraordinarily accurate. You find that sigma xy is n e squared over h with n equal to integer, and the measured accuracy is 1 part in a billion. The point is that this measurement is made in a complex macroscopic many-body state with impurities at different temperatures in different labs with different size, shape, materials, but you always get this exact, extraordinarily accurate current quantization. Why does this happen? How does this happen? This is something which was understood only after it was realized that the conductance is actually related to a topological invariant. And there is a topological explanation of the quantization. So Thouless recognized that the Hall current is actually related to a topological quantum number, like the winding number I talked about, which tells you how many times a curve goes around a point. The actual topology in this here is that the wave functions for each Landau band define a map from the Brillouin zone, which is a 2 torus, to the space of physical states. And one can compute a number called the Chern number or TKNN number. This stands for Thouless, Kohomoto, Nightingale, and some other Ninus for each Landau band. So there is a particular number that you can calculate, which is depending on the mapping. That is just like it's counting number of holes in the torus, right? Number of holes that you have in. And the conductance is actually E squared over H times the sum over C alpha, where C alpha is this Chern number, and the sum is over all the filled bands. For those who are familiar with Berry connection and Berry curvature, essentially for electrons in a solid, the momentum itself provides a natural parameter space, where psi r is e raised to I k dot r u k r. And you can compute the Berry connection, which is like a gauge field, and the Berry curvature, which is like a magnetic field in this case. And what you get is that the Chern number is actually related to the, it's like, this is like a magnetic flux. So the Chern number is related to this overall integral of the Berry curvature over the surface. And since the important point is only that this has to be a number. It's an invariant, it's a number. It can be 0, 1, 2, 3, etc. So this is what leads to the fact that this particular conductance is quantized to a very high degree of accuracy. It only depends on fundamental constants E squared and H, and then a number. It does not depend, it is independent of whether there's disorder or any other kind of things in the system. So what is the consequence of this fact that every quantum Hall state has a topological number attached to it? The most important is what happens at the boundary between topological states. And let me first explain this semi-classically. In fact, the quantum Hall effect also I can explain semi-classically. If I have a 2D sample and I have a magnetic field which is perpendicular to it, we know that a semi-classical picture tells you that the electrons move in Landau orbits. But exactly at the edge of the sample, the Landau orbits cannot complete. So you find that essentially the semi-classical picture is that they have what are called skipping orbits. So the electrons can only go in one direction at this edge. The electrons can move in one direction in here, but all through the bulk of the sample, they're actually, they just go around in circles. They do not contribute to transport. So this is what tells you that the bulk is insulating, but you have transport at the edges. And this transport at the edges is essentially one way. On top, it can go from left to right, from right to left, and at the bottom, it can go from left to right. It is in momentum space. If you plot it,
Can I ask the question?
Sure.
Can you please go back to the previous slide? Yeah, so here the skipping orbits. If we now also draw these circles inside these skipping orbits, the full circles, if you also draw the full circles. So then on the top edge, there is a current from the skipping orbits, which is from right to left. But from full circles inside this space, that current will be from left to right. So will it not nullify it?
No, I didn't understand.
So the current from the skipping orbits is from right to left.
Yeah.
Yeah. So if you draw the similar full circle.
Okay, this is actually just a picture of what you're drawing. What I want to say that this is an orbit which is centered. If you think of it as it can be centered anywhere.
Yeah, but there will be so many orbits.
It's not that that they actually interfere. I mean,
that's
what you're saying. This will.
So there won't be single orbit. There will be a lot of orbits for each electron. There will be an orbit. So the thing is that, for example, in Bohr-van Leeuwen theorem, when we say that there is no magnetism in classical setting, so there we argue that the current from skipping orbits cancel with the current from the total orbits. So that will be from right to left, and this is from left to right. So they nullify. So whether that will not contradict the current from the skipping orbits, the argument.
You want to bring this here and say that this will nullify this?
Yeah, if we plot a lot of these circles, full circles.
No, but actually, I mean the circles are actually just a picture of what is really happening.
Okay.
At the edge, all one wants to say is that there are incomplete. Semi-classically, there are incomplete orbits. Quantum mechanically, you can solve this problem, and what you do find is that you could, like, this is a pictorial representation of it.
Sure. Okay.
So you can, it's not that you can just bring this here and say cancel it, but still, what will happen closer to the orbits, right? Closer to the edge. So it's more like a picture.
Sure.
So I'm not taking it that seriously. So more seriously, it's actually there should only be, if you solve it quantum mechanically, what you say is that you actually have at the Fermi level what are called chiral edge states. This is chiral because E versus K is in one direction. If you plot it at the opposite end, if you plot it at the lower end, for instance, this line will be going from, it will be the other way around. So it will go from here to here. Right? So you cannot have okay, so this is what I'm saying. Sorry, I got a phone call. I was a little distracted. So these are chiral because they are going in one direction. And I was saying at the opposite end, the line would go in the opposite, in the other way round. So that the E versus K would have a different slope, opposite slope. Right? So this is why we know that at each edge there are edge states. The bulk of the states will actually be in the filled band, which is the valence band. And this is the bulk band for which now we've calculated the Chern number, which is, there is something called a bulk boundary correspondence, which tells you that the Chern number in the bulk is related to the number of edge states that you will have. So this is again something which comes from mathematics, which is related to index theorems in the mathematics, which tells you that the Chern number of the bulk is related to number of edge states. As I said earlier, the direction of the flow at both edges is unidirectional and fixed only by the direction sign of the magnetic field, and only the edge states carry current. And the what is it called? The extraordinary accuracy is because you cannot have backscattering between the left and the right movers because they're spatially separated. There's a the entire width of the sample that they have to cover if something has to get backscattered and go in the opposite direction. It's the backscattering which usually causes degradation of the current. So this is what explains the robustness and accuracy of the quantum Hall effect and why it is not affected by impurities or disorder. So the main points of the topological phase that I wanted to emphasize in this is that the bulk is an insulator and the current is only carried by edge states. And coming back to the earlier question, one other way one can say is that in the bulk of the sample, you will have disorder, both around in the bulk and at the elsewhere you will have disorder. So essentially these things will be trapped. These random orbits will get trapped by this disorder. So in terms of, in a quantum mechanical picture, what you have is that you'll have valleys and hills. And these orbits will actually just go around these valleys and hills. Whereas at the edges, they cannot be trapped by disorder because of this fact that you don't have, it just has to go around because there is no way for it to backscatter fully. So that's the normal argument which has to be given in a fully quantum mechanical way. So this is what tells you why it has to be, it's not affected by impurities or disorder. Yeah, so the main points of the topological phase that I wanted to emphasize here are that the bulk is an insulator and the current is only carried by the edge states. And there's quantized transport because there is no backscattering. This quantum Hall effect was initially seen to occur in two-dimensional electron gases formed in a layer of aluminum gallium arsenide sandwiched between gallium arsenide material. So essentially it was like you were just in the lowest state, and so that behaved like a two-dimensional electron gas because it's like a very sharp well. But in recent times, nowadays we can actually make 2D materials which are really one layer thick, and that is in graphene. So people have seen quantum Hall effect in graphene as well. But this topological transport in integer quantum Hall effect happens at very low temperatures and very high magnetic fields. And the recognition that topological phases can exist in bands even without the need for magnetic fields is what has led to the whole new revolution of topological materials in the last decade. So now I'll come to topological materials post 2005, which is all these topological insulators and all these new materials. As I said, I'm just repeating, is basically the realization that strong magnetic fields were not required for realizing topological phases. So the first thing that happened in this field was the prediction of insulating materials with metallic surface states without magnetic field or time reversal breaking. And these were the topological insulators. These were actually materials with strong spin-orbit coupling, and they could behave as if they're like a quantum Hall state. The idea, as I said before, this could not only be in 2 dimensions, but even in 3 dimensions. You basically have materials which are insulating in the bulk, but with conducting edge states. In that sense, it's rather like a block of wood covered with a metal, except the whole thing is actually a single material. In fact, normally you're supposed to stand on an insulator so that you don't get a shock. So there's a joke from R. Shankar at Yale that don't stand on a topological insulator to change the light bulb. One can ask why, if these kind of topological insulators were not discovered earlier, because if now I'm saying that a quarter of the materials in the world are topological, why didn't we see them before? One of the things is that you probably need sophisticated instruments that can map local density of states to know which states carry current, whether the current is going through the bulk of the system or to the edges. Theoretically also, this required understanding of Berry phases and structures of mappings of Brillouin zone to the Hamiltonian, and which means that you need to know more information about the Hamiltonian and just the dispersion or the energy. You need to know much more about the wave functions. And the other important thing which I wanted to mention here is that these kind of effects were predicted first and then experimentally observed, which is unlike the quantum Hall effect and unlike most things in condensed matter physics. In fact, in particle physics, it is common that you normally predict particles WZ, Higgs, etc. before they're discovered. But in condensed matter, normally the phenomenon is experimentally discovered first and then people have explanations for it. So this is one of these unusual cases where it was first predicted. So let me go ahead and try to explain what are these topological insulators. One might think that insulators are the most basic and boring state of matter because electrons are bound to atoms and cannot conduct electricity. Even when the atomic states broaden into bands and you have the occupied states form a valence band and the unoccupied states form a conduction band, you can actually gradually adiabatically move from one to the other. For instance, if you have electrons, the atoms which are far from each other, then each of them have electrons which go around their own atoms and they form an insulating state because they're all separated. But even if they bring them together, they can still form a band structure. They can, the occupied states can form a valence band and the unoccupied states can form a conduction band, and this is still topologically equivalent to the trivial insulator, the atomic insulator, as long as this band doesn't, as long as there is no states at the Fermi energy, there is an insulating gap. And they can be continuously deformed, this can be continuously deformed to this, keeping the energy gap. The gap can become smaller or larger, but the energy gap should remain. That's what I mean by this, that they can, insulators are topologically equivalent if they can be continuously deformed into one another while keeping the energy gap open, not the same. This is just like the donut can be deformed into a coffee cup continuously. The question is, are there phases that are not topologically equivalent to the trivial band insulator? For instance, if an orange is the analog of the trivial phase, then the donut is the analog of a non-trivial phase, which cannot be adiabatically connected to an orange. And we have found one such phase, the quantum Hall state, because here you have a surface state which is at the Fermi level between the valence band and the conduction band. But this, of course, as we already saw, needed strong magnetic field, and it breaks time reversal invariance. Are there topological phases with unbroken time reversal invariance? The first thing people came up with is the quantum spin Hall effect, where they thought that maybe you can have independent or opposite integer quantum Hall effect for spin up and spin down electrons. So spin up electrons can have magnetic field and can have see a magnetic field in this direction. Spin down electrons can see a magnetic field in this direction, and so on an average there'll be no magnetic field. These are theoretical proposals. And then you could have the up electrons going in one direction, the down electrons going in the other directions. But spin is not always a good quantum number. And what if you try to look for some other invariance besides the spin? So then people started looking at what is called time reversal symmetry. In the presence of time reversal symmetry, microscopic laws of physics remain the same if you evolve a system backwards in time. But under the reversal of direction of time, B, magnetic field goes to minus B. The right moving edge states will go to the left moving edge states, obviously, and spin up electrons go to spin down electrons. Turns out in quantum mechanics that the time reversal operator is actually an antilinear operator. An antilinear operator keeps the mod of the inner product fixed, whereas a unitary operator, of course, keeps the inner product itself fixed. And for spin half fermions, the time reversal operator is given by the complex conjugation operator times e raised to minus I pi sy by h cross. And you can check that t squared is minus 1 for spin half particles. Because rotation through 2 pi for fermions, if I do t squared here, you'll get a rotation to 2 pi, and that actually gives you a minus 1. This is what leads to the Cravers theorem in quantum mechanics, which is well known in quantum mechanics, for that if you have for time reversal invariant systems, that is the time reversal operator commutes with the Hamiltonian. For spin half particles, all time reversal invariant states are doubly degenerate. Because for spin half particles, the time reversal operator is anti-unitary, t square is minus 1, all time reversal invariant states are doubly degenerate. The proof of this is that if they were the same state, then t acting on some state will just give you a phase times the same state. But then if I try to do t squared, t acting on e raised to I phi will now give you if I take t e raised to I phi t psi, that will give you e raised to minus I phi t psi, and this will just give you plus 1. But this contradicts the statement that t squared is minus 1. So this tells you that when I act the time reversal operator on a state, and the state, then it has to go to a different state. So if th is equal to 0, what that means is that the energy at the time reversal invariant points, which are k is equal to 0 and k is equal to pi, you always get doubly degenerate states. So energy bands are time reversal invariant because, and for time, which is something which we are imposing on the system, and for time reversal invariant systems, at k is equal to 0 and at k is equal to pi, states have to be doubly degenerate. So this tells you automatically that you have to have there are two classes of possibilities for the states in the insulating gap. You can either have states of this kind that I've drawn on the left-hand side or the ones that I've drawn on the right-hand side. The difference is that I can, all that you have to keep constant, you can move these states around in the gap. But what has to be kept constant is the fact that this point has to be always doubly degenerate. So if I bring this point down here, then I'll have 0, then this whole thing can come below the Fermi level and I'll have 0 states crossing the Fermi level. If I bring this down, for instance, I can have 4 states crossing the Fermi level. The point is I'll always have an even number of bands crossing the Fermi energy in this case. On the other hand, here, if I take this up, I'll still have 1 state crossing the Fermi level. If I do some kind of wiggle this state around so that I do something like this, I will have 3 states crossing the Fermi level, but I will always have an odd number of states crossing the Fermi level. So there is no way that this can be made equivalent to this. So essentially what you realize is that if you have a time reversal invariant system, then there is a possibility that one can have states like you had in the quantum Hall system. These were the kind of states that you had in the quantum Hall system, that you have a single surface state which crosses the Fermi level. So these kind of states are also possible for a time reversal invariant system. So the consequences are that you expect to see edge states like you have in a quantum Hall state. Two states of opposite, the point is because of time reversal invariance, in the quantum Hall state, we had only one such chiral state at one edge, and the other chiral state of the opposite side was on the other edge. In here, you will have two states of opposite chirality at each stage, which are time reverse partners of one another. So essentially, it looks more like this, except that these are now not spin half particles. They don't have a definite spin up and spin down, but they're time reverse partners of one another. And in this case, what will happen is that if I now study the two terminals conductance, I will expect to get 2 e squared by h, because if I put a source on one side and a drain on the other side, I'll have one state from the upside and one state from the downside going on from left to right. So essentially what you have is that this was actually seen in a real experiment. The real material that was used was cadmium telluride and mercury telluride. And when the thickness D is very small, it's actually not a topological insulator. That requires more explanations than I'll give over here. So then the conductance is not quantized, and you got conductance like 0.01 e squared by h and 0.3 e squared by h. But once the thickness is beyond a certain level, then the conductance does get quantized. And for samples 3 and 4, where it was a topological insulator, they found that the conductance was quantized to 2 e squared by h. And more interestingly, people found 3D topological insulators as well. So these can exist in 3 dimensions as well. So in this case, actually surface states, the 3D bulk is the bulk states, and the surface states replies its states as current carrying states, and the bulk states are insulating. And it turned out that the electrically conducting states on the surface were Dirac cones, excitations that obeyed the Dirac equation instead of the usual Schrödinger equation that normal electrons obeyed. People saw that there were real materials, the bismuth selenide, which was an insulator, but exactly at the surface, it had surface states which carried current. And these kinds of pictures were seen by Arpes, which showed picture of energy as a function of momentum and showed that surface states existed and formed the expected surface cone at exactly the gamma point, the 0, 0 point. Lots of new physics could be obtained from these new topological insulators. Because these have a single Dirac cone, they are like basically 1/4 of graphene. And so one can get, for people who are familiar with graphene, you know that when you solve for a Dirac electron in a magnetic field, unlike for the Schrödinger p squared by 2m, p e minus e a squared by 2m psi, you actually get n plus half h cross omega. And in a graphene, you get 4 times n plus half h cross omega, because there's 2 valleys and 2 spins. But for here, it's like a single Dirac cone. So you actually get a half integer quantum Hall effect by applying magnetic field on these surface states of 3D topological insulators. You can get anomalous quantum Hall effect, anomalous quantum Hall effect by instead of a magnetic field, you can deposit ferromagnets and obtain chiral edge states, and at the domain wall you can get some kind of a half integer quantum Hall effect. It's not a quantum Hall effect because you don't have magnetic field, but there's a TR baking by these ferromagnets. It's because time reversal is broken, that's why you can induce a gap. You can get topological spin walls by getting topological insulator with ferromagnets, which may be useful for electronics. So lots of new things come out of these things. I will, in the last 5-10 minutes, I'll just try to explain what are some of these newer things which have come up, including topological superconductors. In this, for as far as these topological phases are concerned, topological insulators and topological superconductors are very much similar. Both of them behave like insulators because they have a gap. They have valence bands and conduction bands. They have a gap to bulk excitations. They can have edge states. And in this phases, the only difference between topological insulators and superconductors are that topological superconductors are particle hole symmetric. That is, for every particle, the conduction band is actually a mirror image of the valence band, and adding an electron to the conduction band is like removing an electron from the valence band. There is a particle hole symmetry. But exactly at zero energy, both these processes are the same, adding an electron and removing an electron. And it happens that if you have a state at zero energy, it does not need a partner state, but it also cannot be removed, because there is, if you want to move it away, you also need to create a partner state, and there are not enough degrees of freedom there. So, how do I say this? Because a zero energy particle is its own antiparticle, you don't have enough degrees of freedom. This has the same number of degrees of freedom as any one of these states, and since it doesn't have a partner, you cannot move it away from zero energy. And in a 1D topological superconductor, what you find is that you can have edge modes. These are like the surface states. In a 1D, the surfaces are simply the edge points. So 1D topological superconductor has Majorana modes at its edges, and this is what actually two of these Majorana modes can form a single fermion. But this is useful for quantum computation, because if these two, the fermion is actually extended in space. So if you do some kind of have disturbance at this, you cannot change the occupation of this state because it is non-local. So these Majorana modes give a new way of storing and manipulating quantum information. The two Majorana modes at the two ends define a single qubit of information non-locally. So it can be immune from decoherence. These are the excitations which obey non-abelian statistics under exchange, which is more exotic. Normal particles are fermions, which are antisymmetric under exchange, bosons, which are symmetric under exchange. Even anyons have a non-trivial phase under exchange, but these actually are more than that. They change their state, and they are not, unlike the anyons, which are still abelian, these are non-abelian. It depends on the order in which you exchange particles. And these could be relevant as building blocks in making quantum computers. So I'm already probably saying things which are just words. So let me end by talking about the current frontiers in the field. Many new materials have been found which are topological. Not only insulators, but also what are called semimetals. Weil semimetals, Dirac semimetals. These are essentially three-dimensional generalizations of graphene, which has a Dirac cone at the Fermi level where the valence and conduction bands touch. You can have higher order topological insulators, which are basically, you can have 2D materials with just corner states, which are Majorana modes. You can have 3D materials which have edge states, which are called hinge states. That is, the edges are 2 dimensions lower than the bulk material. Normally you have a 2D bulk material, it has a 1D surface state, which is the edge of the 2D material, or a 3D material has surface states which are 2D surfaces. For higher order topological insulators, the 2D materials have corner states which are just like at 4 corners, and 3D materials have edge states which are hinge states. People have also found that you can find new topological phases and edge states by shining light on topologically trivial systems. And in these cases, the bands are found to be characterized by other topological invariants besides the Chern number. And the topological phases of these periodically driven systems have been characterized using Floquet theory. And so far, most of these things are in the band structure language, but we know at least one strongly interacting system which has topological protection, which is the fractional quantum Hall state. The fractional quantum Hall state needs electron-electron interactions are important in this to get the fractional quantum Hall state, but it's still a topological system. And generalizations of them called fractional Chern insulators and fractional topological insulators have been at least theoretically studied. And similarly, as instead of Majorana fermions, which are also called icing anyons, people also have parafermions. These have all been, actually the last two things are basically theoretically studied. And a lot of work has gone into looking for Majorana modes, because they're the ones which are supposed to be important for quantum computation. And they, since you don't, they require the original cation model required p-wave superconductors, but people have found ways of making p-wave superconductors by putting ordinary superconductors in proximity to topological materials. Also, they've found ways of making p-wave superconductors by having one-dimensional wires with strong spin-orbit coupling and magnetic field proximity coupled to superconductors, which effectively makes them a topological superconductor. And the current scenario is that there have been experiments by Majorana modes seem to have been seen, and it looks like it has really been seen. I will not talk about my work in this field. I'll just give a picture of some of my collaborators in the last 5 years. These are some of the senior people in other institutes. These are former students of mine who are faculty members. And these are now former students who become postdocs and so on. And these are my current students. And the last row is basically students of all these people above. I've basically been looking at various aspects of these phases, including in the quantum Hall effect, in graphene, silicene, which is a generalization of graphene, wild semi-metal, Floquet-induced phases, topological superconductors, anyons and Majorana modes, and higher order topological insulators. So the main points that I wanted to emphasize in this talk is that now we have a new class of materials which is defined by the interplay of symmetry and topology. In what we earlier knew as insulators, superconductors, metals, now all exist in topologically trivial and topologically non-trivial classes. And even materials in topologically trivial classes can be made interesting in the sense of topological by shining light on these materials. All kinds of exotic excitations exist in these materials. Relativistic particles like Dirac and Weil fermions, particles with unusual statistics like anyons and Majorana modes, and other particles which I have not worked on directly myself and haven't talked about here, monopoles, dions, and axions in these materials. So you basically get exotic particles and exotic effects at low energies. So these are phases which are here to stay for a long time. So it's worth spending time to understand them. Thank you all for coming and listening to me.
Thank you, Professor Rao, for so informative talk on topological phases of quantum matter. Now the presentation is open for questions.
Okay, so I am Sachiraj Mishra speaking. So initially you were saying about some quantum number which is called Chern number.
I can't hear, sorry. Could you?
Hello, can you hear me?
Yeah.
Yeah. Okay. So initially you were saying about some quantum number which is called Chern number. What are its physical significance?
I was talking about Chern numbers.
Yeah.
You see?
So I'm asking the physical significance of Chern.
Hello?
Hello.
Yeah. The difference between Chern number and?
No, I'm asking the physical significance of.
No, what is called winding number. Physical significance of the Chern number is precisely the fact that it is connected to the conductance. Conductances are directly related to the Chern numbers of the how you calculate the Chern number is in terms of it depends on no, the physical significance is that it's related to the conductance. Is that what you're asking?
Yeah. I'm asking how it is.
It has a direct relevance in terms of the conductance. And theoretically, the way it is calculated is that you actually have to look at the band, and then you can, for any filled band, you actually you look at the wave functions. From the wave functions, you can define something called a very connection, an A field, which is defined as psi I del times psi. So given the wave function of all the wave functions that you have in your band, you can define something called a Berry connection, and then for each wave this thing, and then you can sum over all the states which are filled in the band, and you can define this Chern number, which turns out to be an integer.
Okay. For fractional quantum Hall effect, there will be a Chern number corresponding.
For integer quantum Hall effect. For fractional quantum Hall effect, of course, there will not be for fractional quantum Hall effect, it's much harder. You can't calculate it by using band theory and all that because you don't have this. There is okay. If you're asking for how do you do this for a fractional quantum Hall effect, that's much harder. I mean, I don't think you can easily define Chern. It should be 1/3, 1/5 of all these things, but I don't think in terms of Chern numbers, I know how to define that.
Okay. So again, I have a very small question. You were mentioning about some statistics called non-abelian statistics. So yeah, what is that?
I was mentioning about statistics. Yeah, what was I saying?
Non-abelian statistics.
Non-abelian statistics, yeah.
Yeah. So this statistics is applied to which kind of particles? Like Fermi-Dirac is applied to.
Yeah, right now the kind of particles to which it is applied is this Majorana modes, right? Which you can have. I mean, initially anyons and particles with non-abelian statistics like can be studied theoretically. I mean, you can think of them just as particles with certain kinds of quantum numbers and try to study how they will behave under exchange, right? They satisfy the braid. There's something called a braid group. Instead of just having exchange, they get braided, right? Which is true even for anyons. But in the physically, the only kind of particles that are known in the sense that there are experiments which have shown the existence of things which people, I mean, there's a large fraction of people now believe that the experiments can be explained if you think of the particles as Majorana particles. But then you also have to be able to show that you take two Majorana particles, exchange them, and then you get these non-abelian statistics. That if you exchange them once, then you exchange them twice, then you exchange them in different orders, right? That they will not give you back the same answer. So they satisfy braid group statistics rather than the usual just fermions or bosons, right? So otherwise there are no real particles which satisfy non-abelian statistics.
Yes, Sachi, let others also ask. Yes.
Vinod, can I ask?
Yes, sir. Yes.
Madam, when you are talking of insulator,
Yeah.
what you really meant by Fermi energy?
Do I mean what?
Fermi energy.
Yeah.
What you meant by Fermi energy when you talk of insulator?
Insulators, I'm saying
Yes.
that if you have the Fermi
Conduction
energy,
band.
the gap between there is a gap by
That is band
insulators
gap
are
or
just
Fermi
like,
energy?
huh?
That is band gap.
Yeah, that is the band gap. So
Yes.
if there is a Fermi energy is in the band gap, then you will get no current, right? No,
But
there's a band gap.
there are no free electrons. So what is where Fermi energy? What do you mean? There are no
No,
free.
supposing you, I'm saying there is a band gap.
Yeah.
And supposing you look at an energy which is in the band gap.
Yes.
Fermi energy, I'm just using it as a word that I'm looking at some point.
When you are talking of insulator, there are no free electrons. Valence band is completely filled. There is no Fermi level, and then the conduction band is empty, completely empty. So what do you mean by?
But suppose, but now you attach this insulator to say a source and a drain, and then you inject an electron at some energy which is in between in the band gap. Right? There are no states, so you will get zero conductance.
Yeah, that is true. And that energy you are calling Fermi energy.
That is what I'm saying, calling the Fermi energy. Right? So,
if you inject any electron of any energy, and you call that Fermi energy.
Energy of any. Whereas if I have a surface state, then there will be some state.
No, if you add impurities, then there will be electron in the conduction band, and we talk of Fermi energy there.
What?
If you put some impurity states in between, then the electrons will go from there to the conduction band, and we talk of Fermi energy or something.
Yeah, I'm thinking of it in the Landau-Buteyko picture.
What?
That I will inject an electron with a particular source.
Okay, then that makes sense.
Hello, ma'am.
Yes.
Yeah, ma'am, I was doing some literature survey in this topic, and I found that in the topological systems, we are very much concerned to preserve the symmetries like time reversal symmetry, particle hole symmetry, and sublattice symmetry. So, why we are so much concerned to conserve these symmetries?
I couldn't hear. Sorry, let me stop presenting? Maybe I'll hear better. Yeah, what did you say?
Yeah, ma'am, I was saying in the topological systems, we are so much concerned to preserve the symmetries like particle holes, time reversal, and sublattice symmetries. So why we are so much concerned to conserve these symmetries, and is it possible to conserve all these three kinds of symmetries simultaneously in a single system?
No, you don't need to preserve all the symmetries. But usually what happens is that if the symmetry breaks, then the the surface states get gapped out. If you want to look at some of these properties, some of the unusual properties of these topological systems, then you need to preserve, much of what I talked about are what are called symmetry preserved topological insulators. So you have to preserve in a topological superconductor, you have to of course preserve particle hole symmetry. In insulators, you have to preserve time reversal symmetry. In some of all the symmetries. But if you break some symmetry, then it will have some consequences. Is that what you're asking? I couldn't get exactly what you're saying. Because at least the classification is dependent. I mean, you divide topological insulators and all these things depending on what's.
Vinod,
Yes, sir. Yes, Professor Pathak.
can I ask another
Yes.
question?
Yes,
Is
you can ask.
Madam Majorana fermions, do they obey Fermi-Dirac statistics or some fractional statistics? Do you hear me? No,
Professor Rao, your internet is a little bit slow. Your voice is a little bit lagging. Let us wait. Professor Rao?
Is that
Internet is, yeah. Professor Rao, your internet is a little bit weak, I think. Your voice is lagging.
I see. It said that, yeah. It's
Now
going,
it is
but
okay. Now it is
I
okay.
think
Now, okay.
hello. Do you hear? So let us leave. Thanks करिए. Vinod.
Professor Rao?
Vinod.
Okay. So if there are no more
Yes.
questions, so let us thank Professor Sumathi Rao for a wonderful talk today on topological phases in quantum matters. Thank you so much, madam, for accepting our invitation to deliver this excellent talk. Thank you so much. Today in the evening, we will be having a talk by Professor Vikram Tripathi, Tata Institute of Fundamental Research. He'll be talking on looking for Kitao spinons in magnetically ordered phase and MBL approach. So I request all the participants to please log in 10 minutes before the start of the session. Thank you all. Thank you. Thank you, Professor Pathak. Thank you. I can see Professor Navinder and all the participants. I cannot see all the list here. Thank you. Thank you, madam. Thank you, one and all present for today's session. Thank you.
Thank you very much. Thank you very much for having
Yeah,
us.
Navinder.
Yeah.
Navinder.
I think Dr. Navinder
Please do
is
let
back.
me know if you have any questions. I'll be happy to answer.
Yes, yeah. Okay. Thank you, madam. Thank you so much. Thank you so much. Thank you.
Navinder here or gone?
Okay.
He left. Dr.
Okay.
Navinder is left. Okay.
Right.
Thank you, madam. Thank you.
Okay. Okay. Bye.